we're back.
Okay, and we're back. All right, this module, because I don't know if it's going to fit in this week, pumps and pressure carburetors. But before we can start talking about systems that use pressure, we got to first learn about pressure pumps and pressure. And then we can move on to the things that use them. So let's dive right in. Let's see. One. Off to a good start. There are basically two types of pumps. There are basically what you had a question? Two types. I mean, is that on? No, it's not on. Two types of pumps. You get it?
I think so.
Two types of pumps. What are those two types?
Pressure. Regular, extra pressure.
Ones that work and ones that don't work. Constant or positive displacement. I tend to use the word constant. Constant displacement. Or not constant displacement. All right, what are some examples of constant displacement that we've so far kind of worked with in this semester? A what?
Gyrotor.
Gyrotor?
Turbine.
How about the oil pump in an engine? Oil pump, gears, right?
Yep.
Every time the two gears go around, it has to move the stuff around the outside. Positive or constant displacement. It must move. What happens if you block off the exit for a constant displacement pump? Something will break. You will find where the shear shaft is. So we have the gear type, which we saw as the oil pump for the Lycoming, or we could do rotary vane. Rotary vane. So those are the two types. Let me see. I don't know why it's like this, but we'll just kind of. All right. They will displace a given amount. A given amount of liquid for each revolution. For each revolution. If you spin it faster, it will pump more. If you spin it slower, it will pump less. And then we have we can just call it non-constant displacement, for lack of a better term. Non-constant displacement, or even variable. What do we have there? How about Phil's class? Did you have anything that might have been some sort of air pump that moved air?
Axial.
There we go, centrifugal. Or centrifugal.
Yeah.
Yeah.
That's the right way to say it.
All right. When we're talking about fuel pumps, it's really the only types we're going to have. For the most part, we're going to have either the rotary vane or the centrifugal. Once I say centrifugal, it's hard to not say it. So centrifugal type pumps. A good example of a centrifugal pump would be I can see one from here down the hallway, a box fan. A fan, like you sit on your fan, air fan, ceiling fan. That's actually a centrifugal type pump, right? So what happens if you take a box fan is just a house fan, set on the floor, and want me to go get one?
No.
Yeah, it's right there. All right, so what happens if I take and I block off the suction part? We're going to blow it this way. Put a bunch of paper on the back side. What happens? Does anything blow up?
No.
No, just keeps on spinning. No big deal. It can spin the air inside of the fan if it wants to. So it doesn't hurt anything. So same thing with centrifugal pumps for fuel. If you block off the exit with a centrifugal pump for fuel, what happens? Nothing. You just blocked off the exit. That's it. Right? No problems whatsoever. So let me see. Where are you going to find these? Well, in most typical situations for any type of aircraft fuel system that uses pumps, you need two. Why do you need two? Safety and redundancy, right? So, and starting the engine. So you have on the engine the rotary vane type pump, typically. And then somewhere on the airframe, maybe even inside the tank, you would have a centrifugal. So you put it inside the fuel tank, centrifugally pump fuel out. If you block off the exit, no big deal. Doesn't hurt anything. It uses that pump to pump everything up to the rotary vane. The rotary vane is constant displacement, pumps it to the fuel control unit. So let's see, used as boost centrifugal. They are used as boost pumps to deliver fuel to engine-driven pumps. Why would you need that? Well, you need it for starting. Backup for engine-driven. Or engine-driven fuel pump, if that one should fail. They are good for separating air from fuel. Because you'll see in a few weeks, we actually have a system that actually is putting bubbles and stuff back in the fuel. So you want to get rid of that. And they are not constant displacement. We already said that. What else? There's even another reason here. Pump, starting, backup, separating. Oh, yeah.
Gravity feed.
Well, I was thinking increase fuel line pressure to prevent what? Vapor lock. Prevent vapor lock. All right, first thing we talk about is the rotary vane pump. Just like I freaking beg of you to get the difference between a throttle and a mixture, and it's critical to everything, but yet here we are. You have to understand the difference between pressure and volume. Right? Volume is how much something moves. And pressure is pressure. I'm not supposed to use the same word to define a word, but I don't know what else to say. What?
We can use that on the
Use it on the oral?
Yeah.
Yes.
Pressure is pressure.
Pressure is force.
Force. Thank you. So if I brought a garden hose in here.
You'd have water
But would we? If I had all pressure and no volume, what would happen?
Yeah, pressure.
Yeah, very little volume and a lot of pressure. Well, I'd have like a squirt gun, right? Maybe I could reach the back of the room with a little tiny stream, right? That'd be a lot of pressure, but not very much volume. Maybe this is not the best analogy. If I had a lot of volume and no pressure, well, I'd be like taking the end off and it just kind of comes out, but it's like 5 gallons a minute. I mean, I could just get Jennifer really freaking wet and flood the whole thing. But you in the back, be like, I don't care. But if I could build up some pressure, then we have something. So I'm going to talk a lot about that. It's critical that you get it, because if you don't get this pressure volume correlation, then really for the rest of fuel metering systems, they won't make any sense. And you'll always wonder how come they don't make any sense to you. And it'll just come right back to this moment that when I was talking about pressure and volume, you're like, probably isn't important. I'm sure it'll come to me in a dream. So you got to understand that. So, so if you don't know, please ask. Beg of you. Please ask. All right. Before I write notes, we'll just kind of look at this. I think it works best if I just go over it and I go, oh, okay, we can write some notes. So, rotary vane pump. What drives a rotary vane pump?
Engine.
The engine drives the rotary vane pump. Well, just looking at it, what would happen if I attach this to the engine and something happened on the, it's a constant displacement pump, by the way, rotary vane. Something happened to lock up the pump.
Shear shaft.
That would stop the engine, wouldn't it? Something's got to break. Do you want it to break outside the engine or inside the engine?
Outside.
Outside. So the pump breaks right there. Shear shaft. That's why it's so thin right there. They wanted to break right there. Right there. I was working on a Skymaster once upon a time. And the guy complained that his vacuum pump wasn't working. So I pulled the vacuum pump off. Grabbed the new one out of the box, because I was told to, and put it on, and the splines didn't line up. So I was moving the engine propeller, trying to get the splines to move so I could put it in there, but the splines on the engine never moved. So guess what happened? It sheared on the inside. I made a lot of metal inside, yeah.
Would a prop strike be something that would cause that shear?
I've never seen that happen. If it was bad enough, maybe. But there's not a lot of mass to this, so I would tend to be surprised at that. All right, this is a simple version of a vane type pump. Now this could be actually a fuel pump or it could be a vacuum pump. So vacuum pumps work the exact same way. In fact, when I look at it, I'm like, it's basic mechanism of vane type pump. It says fuel pump, so I guess it's fuel. So, all right, so we have the inlet and the outlet. Always got to get kind of orientated here. Inlet, laser pointer. So, fuel's going to come up through here. What's going to bring it up into here?
Your centrifugal pump.
Centrifugal pump is going to pump it up in there. Okay, then this is in the middle, believe it or not, and this is kind of an eccentric thing. So as this black part moves around, when it gets up to here, you can see there's more space. And once you see one apart and running, you're like, that makes perfect sense. Once you see one apart, it's like, oh, it makes perfect sense. You want to look at this?
Yes.
This one's seized up. It's all rusty and seized. All right, so it moves around. So fuel gets in this little cavity. Right there, comes up in here, gets that little cavity. And then as this goes around, right, it's going to lock off and not let any more fluid to come in right about there. And so whatever's in this chamber gets pushed around and out that way. And then there's really not much right here, right, because it kind of closes off. So there you go. It's going to pump that space times 4 every revolution. Spin it faster, you're going to get more fluid out. How much pressure can you get out of this? Or how much pressure would you have?
None right now.
None right now. Why? Well, because it's a drawing.
There's no restriction.
There's no restriction. You got to have a restriction to get pressure. So if I put a pressure gauge right here, tied it off, picked it up right out of there, it would say 0 because there's nothing backing it up to create pressure. Now, if I were to, let's see, right here. There we go, pressure gauge. Right now it's at 0. But if I put a little tiny orifice there, just a little bit, what's pressure going to do? This is going to go way up. All right. So if it was, oh, I freaking hate that. If that orifice was too small, what would happen? What would break? Yeah, it's going to get too much pressure. This can only handle so much pressure in here. So something's got to give. What's going to give? Either the shear shaft, depending on what these are made out of. Sometimes, or a lot of times, these are made out of carbon. So the carbon would just break. So, sometimes they're steel. This one's steel. Which one's that one moving around? Is that
Carbon.
That one has carbon. This one has steel blades. So this one, the shear shaft would go. That one, probably the carbon would shatter inside there first. So that would shatter. So that's how we're going to build up pressure. Got to have an outlet right there.
If the carbon were to
As I as I make that orifice smaller and smaller and smaller, what happens to the flow?
Goes down. The volume.
Constant displacement.
Constant displacement pump. How are you going to make it go down?
Doesn't.
So I'm saying pressure
Pressure goes up.
and volume. Volume stays the same with this drawing the way it is because it's got to pump. Pump's got to pump. And it's going to pump the same amount every single revolution. So if I make that orifice smaller and smaller and smaller, how much comes out? The same. It has to, or it's going to break. Now, this would not be a good application for an aircraft for that very reason. You got to be, because you can't have stuff breaking, right? So you got to change stuff. Okay, we got that? Okay. You sure? Okay. But that wouldn't be a very good application, but that is the very simple version of what it is. This is what it really looks like, more or less. You have to have some way to control the pressure. Otherwise, we just blow lines on the engine all the time, right? You can't have, I know some of you, will say this, but you cannot have, sorry. So I was thinking of this other class, and the student was, it wasn't this one, trust me. And we're talking about generators. And I remember, maybe it was you, and an oral. It was like, well, how do you control the output of a generator? Through the speed. Oh, really? Explain that. What happens if the generator's putting out too much voltage? You slow it down. So, okay, let's take that just one step further. I'm flying along in my aircraft, the generator, at 500 feet. I look over, and I see that my voltage is too high. So that I therefore do what?
Slow down the engine.
Slow down the engine and crash. Hey, it's better than over voltage, right? So by that logic, I have two choices. Now, so supposing I had $100,000 in avionics. Either blow my avionics out or crash the airplane. So every flight, you're going to run me roughly $100,000 in avionics or a new airplane.
You just open up the
And I'm like, does that make sense to me? Yeah.
Or you just cut the feet.
Okay. So, if we want to control the output of the pump, what do we not use to control the output of the pump? The speed of the engine. Okay, it's got to be able to work through all ranges of the engine. All right, within limitations. Thankfully, we're talking about a fuel pump. And when the engine is idling, it doesn't need a lot of fuel. And the fuel pump isn't working very hard or very fast anyway, so that works out. And when we speed up the engine, it means it needs more fuel. Well, guess what else speed up? Pump, so you can get more volume out of it. All right. So this is going to have both a pressure relief valve and a bypass. Those are two different things. Getting better. I realize my slides should be the other way around. I'm like, hey, normally I go there. Okay, so let's start with this in the not running position. Go back to here. We're going back to our stupid pump, right? It doesn't work for airplanes. And starting an engine with a fuel injection system or pressure carburetor is very different than starting with a carburetor. So with the carburetor, you can turn on, like with our test stand, you can turn on the fuel pump because we use a fuel pump on our test stand. And the fuel, because the tank is low, the fuel pump pumps it out. It goes into the carburetor float bowl. And the carburetor float bowl starts filling up with fuel. What happens?
The needle will close the
The float goes up and it
closes
close it off. And the pump is not that much, so it'll stop the flow of fuel. So everything's fine. So you can just sit there and run the fuel pump all day. It doesn't hurt anything. Okay? And then to start it, you typically have either a primer, or if you start it with the butterflies pretty much closed, we know that there's enough vacuum on top of it. It draws fuel out of the idle jets, and you get fuel and the thing starts, right? Okay, fuel injection system is very different. It's closed off from that. The Bendix system does use Venturi and air and stuff, but does Venturi work at idle? No. So we're gonna see this where it doesn't really work so well in idle. You just have to have some springs, and you kind of make it just kind of a dumb thing. Because I don't know, we're at idle, so here you get this much fuel. Continental system doesn't even have a Venturi. It doesn't even measure fuel ever. So it works on a completely different principle. So to start these fuel-injected engines, what you have to actually do, and it's kind of crazy, is you would, everybody does a little bit different. So I bring the mixture full forward, so we're what position? Rich. Take the throttle, I'll open the throttle up. Quarter of the way. Okay, engine's not running, right? Because we're trying to start it. Everybody's with me? Okay, so mixture rich, throttle part way in. I'm going to reach over and I'm going to turn on the electric pump, also called the boost pump. And I'm going to watch fuel flow, because all these engines have a fuel flow gauge. And I'm going to watch the fuel flow gauge, and it's going to do nothing. It's going to start rising. As soon as it starts rising, I shut off the pump. So right there, I was dumping fuel into the engine. Because you can do that. You can override the whole fuel system and just dump fuel right into the engine. And it's not an updraft, these things. They're actually the fuel injections on top of the engine spraying into it. So there you go. Put a bunch of fuel in the engine, then hit the starter.
That's where you talked about that one story with one of your friends said when you asked how long they did the boost pump.
Yeah, like 30
seconds.
Oh, it wasn't more than 30 seconds. Wasn't more than 10 would have been the right answer. Especially if you had a fuel flow indication. So you have to be able to get fuel through the pump, around, into the fuel control unit. When I say fuel control unit, it's just kind of a term that means all of the things, the carburetor, pressure carb, fuel injection system. All right, well, it's not going to get through here because this is what kind of pump? All together now. Constant displacement. So otherwise fuel would come up to here from the boost pump, get to right here and do what? Stop. And do nothing. Right? So I can't get it through, on, and into the fuel control unit to prime it out. So then I can get fuel to here, then I hit the starter. Well, this doesn't move very fast. It's going to start moving slow at the starter, kind of slowly work its way through, and I guess eventually it might actually, it would actually eventually work, provided your battery didn't die first.
Or a starter.
Yeah, we're going to build a starter. And a lot of these engines, because all the fuel injection lines are on top of the cylinders, if you shut it down, you're going to get vapor lock up in those lines. And I tell you all this to say, if you ever see somebody with a fuel-injected engine struggling to get it started, yeah, I don't point and laugh. I'm like, yeah, it sucks. Starting a fuel-injected engine is, yeah, he's not, right? Yeah. It's a challenge.
Yeah.
You got to know what you're doing. And you have to know your airplane pretty well. They're really difficult to start.
It's really easy to flood.
It's really easy to flood, and it's really easy to not flood. So it's really easy to get too little fuel to start. It's really easy to get too much fuel to start. And so you'll learn all about that. Anyway, so we got to have some way for that to work. So here we go. So the pump has a bypass, right? Which bypass can do two things. One, get fuel to the fuel control when the engine's not running. And two, get fuel to the fuel control unit when the pump breaks. Got it? Got to have that. Otherwise, if the pump breaks, you have that other type of pump, just turn on the boost pump, it's going to go right to the pump. The pump broke, and like, well, guess we're going down. Not a good design. So the way this works is, now the pump inlet's on the other side, we turn on the boost pump. Fuel would come in here. It doesn't get through here, does it?
No.
Okay, it can't. So it comes up here. There's a very weak, just say weak, thank you. Very weak spring. I know that because it says that. And some holes right here, and the fuel just pushes it down. That spring is so weak, it's only designed to hold that plate up. It's just enough to hold it up. It's all it's there for. And so the fuel comes in here, pushes that plate down, bypasses the pump, and out it goes. Follow?
Yep.
Okay. That can be good, that can be bad. So in the Continental fuel injection system, it uses a pump. I don't want to get too far ahead of us, but the whole system is based upon how fast the engine is running, and it's calibrated to that. So if you override the fuel pump, then you've overridden the brains of the operation. So in a Continental, you can actually overboost the pump and flood the engine. So that's a problem. So you got to be careful with that. But Lycoming system, you give it all the fuel you want, it'll deal with it. You'll see through the diaphragms and stuff. So that does two things then. The bypass does two things. What are the two things? One, okay, fuel through when it's broken, and two, fuel through to start. Okay. Then once it starts, boom, fuel's going to come through here, go through the pump and go out this way, out the pump. But this is kind of the pressure sensing port right here. So remember that little plate that was down here?
Yeah.
That was barely hanging out? The pressure from the pump throws it up and slams it into the top of this thing. It ain't coming down now because the pump's holding it up. All that pressure here is holding it up. All the pressure here is going to push it and hold it up. Okay, then it's going to take this piece right here and turn it into a pressure sensing unit, pressure bypass. So we've set this up. It's got a much stronger spring here and typically a diaphragm up here. We're going to talk about all that. And so what happens if I were to block off this outlet? Before we had a pump that would break, right? Okay, now it's not going to break. It's going to come up through here, hit there, come up, back through here, and go back to the side of the pump. So you can sit there and do that all day. Comes up, pushes on this plate. This plate goes up, pushes against this spring. That comes around. Now, if I want more pressure, well, we'll do this now. But why would we want that? I mean, there's some situations where you effectively do have something like that. The fuel control unit's off. Don't let any fuel through. That's exactly what happens. But we'll put an orifice here. If we put an orifice here, that means we're going to have some restriction, which means now we have pressure. Okay, so fuel goes through here. We get some coming out. I think, well, whatever's coming out, I want more pressure. So what do? Tighten this up, put more pressure on the spring. That wants to force this down. It takes more pressure to push it up. Therefore, the entire pump just got more pressure. I want less pressure. I unscrew this right here. That releases the pressure on the spring. It makes this easier to go up, and the entire output of the pump pressure goes down. So you have this pressure right here. Got it? Mm-hmm. Okay. I'll talk about it later. All right. Now, I told you there was a diaphragm. You can add a diaphragm to this. Now it's called the compensated fuel pump. Compensating means sounds like he gets money for doing this. It doesn't. So what happens is we have this diaphragm right here. We added the diaphragm. And if I put, so there's no fuel up here. No fuel. What's up here? Air. Okay. Trying to make this easy. If I add air pressure up here, does it help the spring or take away from the spring? It makes the spring stronger. Okay. So what you can do is you can port air into here to make this stronger and assist the spring. If I make this stronger and assist the spring, what happens to the pressure of the pump? Pump pressure goes up. Okay. So why would we ever want that? I don't know. Is it Tammy down here? Let's just say we have a turbocharger. And turbochargers tend to lag behind everything. If they're big, smaller ones can spool up pretty fast. But the bigger they are, the longer they take to spool up. So we'll talk about turbochargers in a few weeks. But add the throttle. Whoosh. Engine goes. Engine goes. We're looking for faster, maybe?
Faster.
You guys, are you with me over here? Did I lose you a while back? And you're like, engine go? I don't know. I don't know what happens. What happens when you push the throttle in? It goes faster. Okay, you need more air, you need more fuel.
Yeah.
All right? How much fuel you need is a function of how much air you have. We have a turbocharger. Turbocharger is slow to react. Right? Engine sped up. Need more fuel. Yeah, it's some more fuel because it's sped up. Now that exhaust gas is going to go around. It takes a while. Turbocharger's like, kind of, what's going on? Like, hey, we're speeding up over here. Speeding up. Oh, okay. So it takes a minute. It starts speeding up. Now when the turbocharger spools up, it starts compressing more air into the engine. What do you need? More fuel. Well, thankfully, one of the ways we can do that is through this to help out a little bit. So the engine speeds up. Turbocharger lags. There's just low pressure in here, in the top. All right, so the pump is going to have a certain amount of PSI. And that PSI is fine, delivers to the engine. Now the turbocharger starts spooling up. Now here comes the pressure. Now we need more fuel. Well, at the same time, we just vent it to right here. So this senses like supercharger or turbocharger pressure. And when it spools up, then this will assist the spring push down what happens to the pump pressure. Now the pump pressure goes up. We get more fuel going on to the engine, which was what we wanted to begin with. So something along that line. Oops. I don't want to do that. Okay. Compensated fuel pump. This is the actual diagram of the pump that you're going to be working with, which is the actual cutaway that's over there. So everything here is pretty much what we just talked about, but laid out just slightly different. So what do we got here? Rotation, carburetor. Why are there two pictures here? Because one is on, one is off. Let me see. It's plugged off. Fuel to carburetor, rotation. Line from supercharger, vent. Oh, they're right here. Got the vent line, no vent plug. Got it. Bypass, no bypass. Oh, we're in bypass over here, I think. Yes, we are. So it looks like we're in bypass over here. So this one is not running. Yeah, okay. Could have read that. That would have been fun. All right, so we're going to start with this one over here. Engine is not running. Fuel comes through here. Does it go through the pump?
No.
No, why not? Because it can't, because it's not running. All right, so it's going to come up here and go through this, and there's a plunger-looking thing right here on a very weak spring. And so it pushes that aside and just finds its way right through without any problem whatsoever. All right, once the engine starts and this starts spinning, oh, when will this close, by the way? That's going to be my questions. What pressure, or when does that bypass close?
When the pressure is greater at the pump.
Which pump?
The main pump.
When the vane pump exceeds the boost pump.
Makes sense.
The very second that this pump here, the engine-driven pump, exceeds the pressure of the boost pump, then, because this is outlet right here, so when this outlet pressure right here starts to increase over the boost pump, it'll come up into here and push this closed. And so then this takes over. So that's what happened over here. So we started the pump going. And the output pressure was sensed back here, was greater than the boost pump, and closed this. So the boost pump could still be running, doesn't hurt anything. So close that. Okay, now we're in our closed loop system. So it comes through here, goes around the bottom, and out. Well, we set our pressure regulator up here and want a certain amount of pressure. And if it exceeds that amount of pressure, this fuel comes up here. It pushes up on this little plate right here, which pushes up on this diaphragm, which is also attached to this spring. And it comes up and around and back down. So it opens up the bypass. Looks like there's two back. Opens up the bypass, comes back around, just recirculates. The screw is a funny thing right here. It has left-hand threads. Why?
Why?
And this is never fun for me on the oral. So which way, if you had to design something,
Right hand.
and you had to design it so that if you turned it one way you got more pressure and you turned it the other way you got less pressure, which way would you want to turn the screw on top to get more pressure?
Righty tighty.
Which way do you want to go? To the right or to the left?
Right.
To the right to get more pressure. I would too. And if you wanted less pressure, you would
This is the left.
like you're loosening up. Let's think about what's happening inside. It's left-hand threads. So as I screw it to the right, inside is left-hand threads. So what is that nut doing?
It's coming out. Yeah.
It's coming out. If it comes out, which way is it pushing on the spring?
In.
Is it pushing down on the spring?
No, pushing out.
If I turn it to the right, righty-tighty. Think about a nut, left-hand nut on a bolt. I got a bolt here,
Yeah.
right? If I turn it to the right, it's going to pull the bolt on.
Yes.
If I turn it to the left, the nut's going to fall off.
Yes.
Yeah.
Okay, but what if it's left-hand thread?
If you turn it left.
As I turn it to the left,
It
It's gonna
tightens.
pull it.
it's going to pull it in, And if I turn it to the right, it's going to go back out.
Yes.
Okay? Now we're going to take this left-hand thread, we're going to put it out this way, and there's a spring right here. So if I turn it to the right,
It's gonna push on it.
Turn it to the right, it's gonna come.
turn it's going to come down because it's left-hand
It's
thread.
gonna push on.
It's loosening up.
Yes, right tight.
It's righty loosey.
Yeah, righty loosey.
Yeah, but
Righty
it's
loosey.
tightening the spring basically.
It's tightening the spring,
So right.
but it's making the nut drop down.
spring.
Okay, so there's
Yes.
Okay, one more time.
Thank
As if I was 8 years old.
It should just
love
look
her.
like-
Thank you. Suppose 8. Righty tighty, lefty loosey is what we practice. You go to the right, tightens up the nut. Go to the left, loosens the nut. Okay, but when we're working on the pump, we want to go to the right to make more pressure. So this is left-hand threads, which are backwards from normal. Everybody with me so far?
Yeah.
So when I turn it to the right, instead of righty-tighty, it's righty-loosey.
So it's the opposite of right.
Opposite.
That's exactly right.
It's righty-loosey. If we're talking about a bolt. So righty-loosey means that as I turn this to the right, like I'm thinking I'm tightening it, and you think you tightened this nut to come up on it, right? But you're not. You're making the nut fall down. So this nut right here, as you turn it to the right, it goes down, putting more pressure onto that spring, which puts more pressure on the diaphragm.
It's still righty tighty, but just for the spring, not for the nut.
Yes.
So righty tighty for the spring.
If you can remember nothing else, then you can remember this maybe. When you turn that screw on the top, where's my pump going around here?
Right there.
When you screw this in to the right,
Increase pressure.
you increase the pressure.
Yes.
And when you turn it to the left, you decrease pressure. And I'll say something like,
Why?
yeah, it's left-hand thread. You're like, yeah, so what?
So during the eventual oral, we could just say it doesn't matter, other than the fact that you just know that it increases pressure if you turn to the right.
Yeah.
Yeah.
See how it's backwards?
You don't need to hit
So once you see it, and so when you screw it to the right, the nut's going to drop down, putting more pressure on the spring, which is going to increase pressure. Now, let's see if this is the first class that can get through an entire year without somebody saying, so how do you increase pressure?
Got it.
Well, it's left-hand thread. You go to the left. And to that I say,
Pushing
Yeah,
it
but
back
we're-
and forth.
Tell me more.
I'll see you tomorrow.
Explain it.
You can, we'll talk about this tomorrow.
What do you mean by that?
All right, that's all there is to it. All right, I've explained everything.
Oh, thank God.
There's not much more to it.
Let's
Let's go test.
Yeah, see, it's the end of my slides right there. All right.
damn.
Test tomorrow?
Yeah.
All right. Let me see. What was that about?
All right.
Well, I guess we're done for today. Huh?
Tighten the spring.
There he goes.
Okay. Well, you want me to write? Want me to write notes or move on?
Move on.
I think so.
Rotary vane pump. She doesn't want. She just wants me to move on. She's like, I got this. What kind of pump is it?
Rotary vane. Cause of displacement.
Well, you're recording, right?
Yes.
Yeah.
Actually, I didn't know.
Yeah, no, nobody reminded me.
Yeah, that's.
Oh, we kept him from reminding you, trust me.
So we'll deliver a constant volume
Whoa.
fuel per revolution. Two, a pump does not pump pressure. A pump does not pump pressure. What does it pump?
Volume.
Yep. What do we need to get pressure?
Restriction.
A restriction in the outlet causes pressure to build. Causes pressure to build. If restriction is, which I'd say, opened,
Did you want to see this?
pressure goes
So,
down. If restriction is closed, more, C-L-O-S, closed. It's not easy to talk and do it at the same time. You kind of forget where you're at. Pressure goes up. All right, super students. What happens if I got my pump and now we're talking about the rotary vane pump that we're working with. And we have to keep in mind how it actually works. So that's a very general statement. If the restriction is opened up, pressure goes up, pressure goes down. That's only in a pump without a pressure relief valve or without a pressure regulator. We have a pressure regulator. So, go off script here. But if pump has a pressure regulator. Okay. If restriction is opened, pressure goes what?
Down.
Goes the same.
Oh.
If restriction
The regulator.
is closed, pressure
Stays the same
stays the same
Or does it stay the
Incredible.
same?
because of a regulator.
because the regulator. I'll show you. If pump is sped up, pressure what?
Stays the same.
Stays the same. If pump slows down, I hope you're seeing a pattern. Pressure stays the same. All of this is to a point. At some point, it's not. The rules are going to change. But the rules are pretty. It's more or less an extreme. So we can talk about that after break.